Okay, so this is Calc 2, working with differential equations, and now I want to introduce another special type of differential equation, the logistic equation. Okay. So the drawback of our exponential equation was that it wasn't realistic. It doesn't have a top to it. So if you think of the change of a population, you wouldn't expect it to grow indefinitely. You know, eventually the population will consume all of its resources or something of that nature, and it's you know, it'll grow beyond the petri dish, so to speak. So what we have now is the logistic equation, which has a limiting capacity on it. So here is the logistic differential equation, and it looks like this. dy, the change in the population with respect to time is proportional to the population times this extra constant bit, where you see if the population exceeds the limiting capacity, this will turn to a negative constant, which will mean that the population will be decreasing. So as long as the population is less than this limiting capacity, this factor will be positive and the population will have a growth to it. Okay, okay, so what? L is the carrying capacity, and K is assumed to be greater than 0, and L is also assumed to be some number greater than 0. Okay. So the first thing we'll do, just like what we did with the exponential version, is to solve this differential equation. So the one we worked with before in the previous section was that the change in population is proportional to the population, and that gave us the equation y equals ae to the kt, which you probably are familiar with from physics and chemistry and that sort of thing. This is our new differential equation, the logistic differential equation, and we'll want to now solve this so we can get a corresponding solution like we did with the exponential guy. So here we go. They do this in example 1, and they use a technique that we worry about later called partial fraction decomposition, which is actually in section 8.5. But you probably saw this in your college algebra. Well, I hope you saw this in your college algebra class. You may not have. Okay, so what we'll do is take this, we start here, and then we're going to separate this guy. I like to leave my constant on the right. So I'll end up with dy all over y times 1 minus y over L, and that'll equal k dt. Okay. So to deal with this, first I'm going to factor out an L, in particular 1 over L, so I'll end up with 1 over L times y times L minus y, okay, and that equals k dt. And then 1 over L, 1 over 1 over L is the same as just plain old L. So it'd be L dy all over y times L minus y equals k dt. Okay, and now they do this partial fraction decomposition, which is basically just a way of undoing finding a common denominator and adding together. Okay, so what we'll do is break apart this fraction, and the end result, which may be kind of mystifying at this point, but the end result will be 1 over y plus 1 all over L minus y dy, and that'll equal k dt. So if you've not seen partial fractions, we'll do it later, but for now, just please trust me that this is equivalent to this. Okay, so now it's broken down into that form. I can go ahead and integrate both sides. So I'll have the integral of 1 over y plus 1 over L minus y dy equals k dt, integral of k dt. Over here, the first integral, 1 over y, is just the ln of the absolute value of y. And then the integral of this thing, if you do a quick u sub, you'll see you have a negative floating about, right? So u, if you let that equal L minus y, your differential du will be negative dy, which implies that dy is negative du. Okay? So your integral will become plus the integral of negative du all over u. Of course, on the right-hand side, we have kt plus c. This then is just our natural log integral. So you have the ln of absolute value y minus the ln of u, and of course u was L minus y, and that'll equal kt plus c. Then we could use properties of logarithms to combine these guys into the ln of the absolute value of y all over L minus y equals kt plus c. And then we kind of clown around like we did with the solving the exponential growth equations. So you want to exponentiate both sides. This, of course, will become absolute value of y all over L minus y. Over here, you'll have e to the c times e to the kt. Drop the absolute values, and you can replace this e to the c with a constant, if you wish. So a big C. So I'll have y all over L minus y equals big C e to the kt. So we're getting there. I want an explicit equation here, y equals something. Okay, so I'm going to multiply both sides by L minus y. I'll get y equals L ce to the kt minus y ce to the kt. And move all the y's on one side, so y plus y ce to the kt equals L times ce to the kt. Factor out the y, you get y times 1 plus ce to the kt equals L ce to the kt. Divide both sides by 1 plus ce to the kt, and you get y equals L ce to the kt all over 1 plus ce to the kt. All right. So if you've seen the logistic equation before, you know that's not it right there. What we'll do to get it into that form is multiply top and bottom by what do I want to do? 1 all over c e to the negative kt. Okay, so it would be 1 all over c e to the negative kt here. And doing so, I'll end up with y equals, so this times this and this will cancel, and you just have L, the limiting capacity, all over 1 all over c e to the negative kt plus 1. And then we're going to replace this 1 over c with a general constant b. Okay? So we'll just say that's b, and use the commutative property of addition to rewrite that as 1 plus b e to the negative kt. And then that's our traditional form for the logistic equation. Okay, so if you were to look at the graph of this thing, it's going to have this sort of S-shaped flavor to it. The L value is kind of where it's approaching as t goes to infinity. So you can actually say the limit as t goes to a very big number, infinity. We haven't talked, did we talk about infinite limits? We probably did, Calc 1. But that'll be 1 L over 1 plus b e to the negative kt. And that'll be just L all over 1 plus the limit of this thing as t goes to infinity. And of course, this part will just be 0. So what you end up in the end of the day is this thing, as t goes to infinity, the population will go to the limiting capacity, L. Okay. Okay. There's some problems that will really challenge you and try to have you uh, play around with the form of the logistic equation. And also they, of course, want you to verify solutions to these things. So problem 7 requires a bit of tricky algebra. Let's look at it. Verify the equation satisfies the logistic differential equations. Problem 7. Of course, the logistic differential equation, dy over dt equals ky times 1 minus L over y. And then the potential solution, y equals 12 all over 1 plus 6e to the negative t. All right. So it's your standard, start on the right-hand side, go to the left-hand side. Let's get the derivative of y. It'd probably be easier if we rewrite it and use the product rule. So 1 plus 6e to the negative t to the negative 1. Sorry for smushing that in there. But the derivative of this is what we're after. Y prime equals negative 12 then times 1 plus 6e to the negative t. Now to the negative 1 minus 1 is negative 2 times the derivative of the innards, which is negative 6e to the negative t. Right? We could rewrite that then as, and I kind of don't want to multiply too much of it out for reasons to be determined later, because you could rewrite the derivative in terms of the original function, and that's going to be the key. So you can rewrite this as negative 12 all over 1 plus 6e to the negative t, and then times negative 6e to the negative t all over 1 plus 6e to the negative t. All right. So this is going to be the key to showing that it fulfills the differential equation. All right, so that's my given information, and I'll go at it now. So I'm going to starting on the left-hand side. I note what? So I note dy with respect to dt from the given information is negative 12 all over 1 plus 6e to the negative t times 6e to the negative t all over, and I'm going to rewrite it a little bit, 6e to the negative t plus 1, okay, for reasons to be TBA, right, to be, or TBD, to be determined. The reason why is because now this thing right here is just y. So I'm going to need to rewrite this thing in this form, and you could do that via the gateway to doing that is by adding and subtracting 1, or doing long division is really what you're doing. So anyways, negative 12 all over 1 plus 6e to the negative t times, and one trick to it is just writing 6e to the negative t plus 1 minus 1 all over 6e to the negative t plus 1. And then when you butterfly it, or you fillet it, you're going to get that 1 minus this thing. So 1 minus L over y, hopefully. Okay, so let's do that. I get negative 12 all over 1 plus 6e to the negative t. Let's just write that as y, because we could do that. Actually, there's a negative floating about there too, so that is going to cause a little bit of trouble for me. Oh, it's a negative times a negative here, so that's actually at the end of the day, it's a positive. Sorry about that. This is positive. Okay, so anyways, ultimately this is y. The k value, you can just say k is 1. Okay, so this is, we'll say 1 times y times this thing. We're going to, like I said, we're going to butterfly it. This over this is just 1, and then minus 1 all over 6e to the negative t plus 1. Okay, and then this thing looks suspiciously like y, except it's missing that numerator of 12, and that's an easy fix. So you can go 1 times y times 1 minus multiply it by 12 over 12, right? So you'd have 1/12 times 12 all over 6e to the negative t plus 1. And, oh, did I write this original differential equation wrong? Yeah, I did. This should be y over L, sorry. Did I write it wrong in the beginning when I first did it? No, I didn't. So it's right back here in my notes. I just flipped it. So a bit of upside down that I screwed up. Okay, so there's that. So what am I doing? It's 1 times y times 1 minus 1/12 times y, so it'd be y over 12. So at the end of the day, your limiting capacity here is 12. Your k value is just 1, and it does, you know, this equals the right-hand side of the differential equation, which is what you want to show. So which is the right-hand side of the differential equation. Okay, so there's that. A little bit of tricky business here with some of the algebra, but hopefully I didn't lose you. All right, let's proceed to something bigger and better. Number 15, here we want to find the k value, the growth constant, part A. Part B, we want to find the limiting capacity. They want you to graph the thing. We'll just sort of do a graph by hand and determine the p value, part D. Determine where the population growth is the greatest. So it's not necessarily when is it the greatest, it's what is the population such that the growth is the greatest. Okay, so they're going to give you a nice differential equation, a logistic differential equation, 0.1p minus 0.0004p squared. And then you're going to have to identify the bits and pieces, so it's not really in their standard form. So first things first, we'll factor out a 0.1 and then a p. So this would be like our k times a y. And then we have 1 minus this divided by 1/10 is the same as multiplying by 10. So it would be 0.004 times p. Okay. So rewriting that then, so I could easily identify the L value. It's 1 minus p all over tenths, hundredths, 4 1,000ths is 1 all over 250. Right, so it'd be p all over 250. So part A is k, the thing in front of the p there. Part B, then the L value looks like 250. To graph it, we can sort of guesstimate its figure. It always have that S shape to it, and its limiting capacity is at 250, so we can mark 250 on the graph. And it should look something like that. Okay, so part C, the graph. To find part D, what you're trying to do is maximize this equation, basically. So to maximize an equation, what do you do from calculus 1? Well, you find its derivative, you set it equal to 0, get the critical points, do your sign chart, and see where it's going negative, positive, right? Because then that'll be a max there. Okay, so in this case, I just sort of pretend this is my function and find its derivative. In other words, you're finding the second derivative of this thing. Okay? So part D, the second derivative of this will be dp squared all over d squared, d squared p all over dt squared. I always forget how to write the second derivative in this notation. That'll equal what? So the derivative of this thing, and you do it implicitly, Okay, so it'd be 0.1 times the derivative of p is 1 times p prime. So you get p prime, and of course there's a 0.1 there. And then minus, bring down the 2, so you'd have 0.0008 p times another p prime. Okay. And then we want to set that equal to 0 and factor out a p prime. So 0.1 p prime times 1 minus 0.008 times p. Right? And this thing right here will give us two sort of trivial solutions. It's if you're setting these parts equal to 0, when I set this equal to 0, it's equivalent to looking for where the first derivative is equal to 0. And the first derivative is sitting right here. It's equal to 0 when the population is 0 or when the population is equal to 250. And both of these are just straight line solutions. Okay, when the population is 0, it's not going to have any change. The change in the population will be 0. When the population is 250, then this factor will be 0. It'll be 0.1 times 250 times 0, which will give you 0, and there's no change there. Okay, so these are kind of constant solutions which we kind of throw out in this case. All right, it's not going to give us what we're looking for when a population where the growth is the greatest, because in those are just these solutions here, this line here and then this line here. We're interested in finding this point basically, where the rate of change, the tangent line to this curve is the greatest. Okay, and that'll be right there. But anyways, what that comes down to, the big and the small of my ramblings, is find where that thing is equal to 0, and that will be your solution, so to speak. So I take 1 minus 0.008 p, set it equal to 0, and solve. So you get p equals 1 all over tenths, hundredths, 8 1,000ths, which is equal to 125. It's no coincidence that that thing is just L all over 2. Okay? In general, that will be the case. The population such that the population's rate of change is the greatest will be when you're halfway in between 0 and the limiting capacity of your population. Okay? So this is where the population's rate of change is the greatest. It's not where. Obviously, some of the problems in the book ask, sorry, it's not when. Some of the problems in the book ask when. This is where. So yeah, let's look at one more application, and it'll have some Euler's method involved as well. Okay, so here we go. This is number 31. They give us the limiting capacity is 200. The initial condition or the initial population maybe is 25. And then the population at time 2 is 39. And if you want to spice things up, you can always think of these in terms of zombies. And so the limiting population, 200 zombies max. In the beginning, you had 25 zombies, and after 2 days, you have 39 zombies, right? And the problem is asking for an equation that tells you how many zombies you have at day whatever. They want to know how many zombies you'll have at day 5. They want to know, what else do they want to know? When will the number of zombies be half the limiting capacity? So when is the number of zombies equal to 100? Then they want you to use Euler's method to approximate the number of zombies at day 5. And then they want you to figure out the when the rate of change of the zombies is greatest. In other words, when is it really, really not a good idea to go outside? Okay, so that's the spiel. Part A is just to get the logistic equation for this scary scenario, and our logistic equation will always have the form L over 1 plus B e to the negative kt, and so we know L, and then we just kind of chase down the unknown variables using the given information. Okay, so first use 0, 25. So 25 zombies in the beginning. We don't know how that happened. Maybe a scientist was experimenting on humans and was experimenting on 25 soldiers or something and injected them with some weird virus, and now we have 25 zombies, right? So 25, when I put in 0 for t, k times 0 is 0, negative 0 is just 0. So that was 200 all over 1 plus b. E to the 0 is 1. You can cross multiply here. So you get 1 plus b equals 200 over 25 is 8. So therefore b is 7. Okay, so we got one variable down, and then we have to get the growth constant. Y equals 200 all over 1 plus 7 e to the negative kt. So now I use the other point to solve for k. And what do you have then? So there's 39 zombies at day 2. So 200 all over 1 plus 7 e to the negative 2k. And I want to solve that for k. So again, you can cross multiply. We get 1 plus 7 e to the negative 2k equals 239ths. Subtract 1 from both sides, 7e to the negative 2k equals 39, 161 all over 39. Divide both sides by 7. E to the negative 2k is 23 39ths. And then take your natural logs on both sides. You end up with negative 2k equals ln of 23 39ths. Divide by negative 2. K equals negative ln of 23 over 39ths all over 2. You can get an approximation. I usually just leave it. Be careful when you do put it into this logistic equation. It's negative of the k value. And right now it already is negative, so when I pop it into here, it will end up being positive. In other words, my official logistic equation is y equals 200 all over 1 plus 7e to not the negative, but now the positive, ln of 23 all over 39 all over 2 times t. Okay, so there's that. They want to know how many zombies you'll have at time 5. Okay, so part B, zombies at day 5. Okay, so that's easy. Just plug 5 in for t. So y of 5, and you can go to your calculator, and you'll see it's 70 zombies. Part C, they want to know when the heck are you going to have 100 zombies? Okay, so you just let the y value be 100. On the other side, I have 200 all over 1 plus 7e to the ln of 23 37ths all over 2t, and then solve for t, right? So that should be just a matter of doing some pre-calculus. We can cross multiply again. End up with 1 plus 7e. Let's just write k for now, and then we'll back substitute. Kt equals 2. Subtract 1, you'll get 1. Divide by 7, you'll get 1/7. Take the ln of both sides, and you'll have the ln of 1/7 equals the ln of e to the kt. Bring down the kt, and you'll have kt ln of e, so you just have kt and then divide by k. So t equals ln of 1/7 divided by k. All right, then if we back substitute our k value, we'll get 2 ln of 1/7, and I believe our k value was negative all over the ln of 23/37. Okay. If you plug that into your calculator, then, oops, and this is positive, sorry, it was, yeah, so this isn't really k, it's negative k. Okay, so negative, sorry about that. So skipping too many steps at once. I promise I won't do that again. 7.37 days. You'll have 100 zombies. Okay, part D then, they want you to use Euler's method to get an approximation for the number of zombies at time 5. And they want you to use a step size of 1. Okay, so they want you to let n equal 5. Your h value, they want to be 1. And our differential equation, we're going to need that for this. dy with respect to dt, or if you'd rather, the change in z for zombies. But anyways, it'll be k times y times 1 minus y all over L, and then fill in the blanks, right? So k we found to be that big ugly thing from before. K was negative ln 23 over 37 all over 2, and then times 1 minus y all over L. Limiting capacity is 200 zombies. Okay, so we do a chart. I'm going to give myself a little bit more room for this. And we have our n, we need t, and then we need y, the number of zombies. This is Euler's method. I'm starting at 0, and at time 0 we have 70. Sorry, at time 0 we have, how many did I say? 25 maybe? 25 zombies. Oops, sorry about that. Okay. And then we want to go to 5, and our increment value, or h value, is 1s. So we can go ahead and fill that in. Okay, the Euler's formula, again, in case you forgot, x sub n will equal x sub n minus 1 plus our h, and then y sub n will equal y sub n minus 1 plus h times our differential equation, which we write as a function of 2 variables, x sub n minus 1 and y sub n minus 1. Okay. Okie dokie. So let's start. Our x sub 0 is 0. Our y sub 0 is 25. And then x sub 1 will be 1. And we should just be using t's, right? So it's t of n and y sub n. This should be t sub n equals t sub n minus 1. This is t sub 0. This is t sub 1. Okay. So at t sub 1, y sub 1 will be the previous guy, y sub n minus 1, 25, plus 1 times the differential equation evaluated at the previous point. So remind myself what that differential equation is. It's this thing right here. So I'm plugging this previous point, t sub 0, y sub 0, into this expression. So I'll have negative ln 23 over 37, oops, geez, negative ln 23 over 37 over 2 times 1 minus y sub 0, which is 25 all over 200. Okay, so it's that big ugly thing. And then if we evaluate that, we get I believe 30.78-ish. Okay. So this will be 30.78 0.78 in our table. And then we go to the next one. So when t sub 2 is 1, y sub 2 will be the previous guy, 30.78, plus 1 times this thing. So negative ln of 23 over 37 all over 2 times 1 minus the previous 30.78 all over 200. And I believe we get 37.65 for that guy. And this t sub 2 should be 2 now. 37.65. And then t sub 3 will be 3. Okay, so go back to my chart. I got 37.65. When t sub 3 is 3, I get y sub 3 is 37.65 plus 1 times negative ln 23 over 37 all over 2 times 1 minus 37.65 now over 200, which should be approximately about, did I miss something? Yes, I did. I missed the y value should be wedged in here. Geez, sorry. I won't screw that up in class, I promise. You need your y value here. The y value from before is 25. Then I need to wedge the y value in here is 30.78. And then wedging the y value in here, 37.65. And you should get approximately 37.65, 45.72. Let's just do one more to make it clear what this formula is. Y sub 4 will be 45.72 plus 1 times negative ln of 23 over 37 over 2. But then you'll have to remember the y is in there as well. So 45.72 times 1 minus 45.72 all over 200. Okay, my numbers were wrong. I just had forgot to write this in. These numbers are right. Sorry. I just forgot to wedge that in there. Okay, so anyways, y sub 3 will be 45.72, y sub 4 will be 55.03, and then our approximation for day 5, the number of zombies we think is around 65.57. If you look back in our notes, we said the exact number of zombies should be 70, okay, approximately 70. So it should be close. It's just our H size is so big that we're not getting super close. Okay, so anyways, the Euler method again, just for review. The last point then is finding when the number of zombies, the change in number of zombies is the largest. So part E, when is the number of zombies changing the quickest? And again, what this comes down to is finding the inflection point. You take the derivative, find the second derivative, set it equal to 0, and that will give you the point where it's changing the greatest. And we noted before the population where this will happen is L over 2. Okay, so we could plug that into our logistic equation and solve out for the time. Okay, so L over 2 is 100. We have that equal to 200 all over 1 plus 7 e to the whatever the heck the k. You know, we have this negative k value times t. And then solve this. So cross multiply. We'll get 1 plus 7 e to the negative kt equaling 2. Subtract 1 to the other side, 7e to the negative kt equals 1. And we've already done this, right? We know it's about 7 something, 7 point something. Anyways, divide both sides by 7, e to the negative kt equals 1/7. Take the ln of both sides, you get negative kt equals ln of 1/7. Did we already do this? It seems like we should have in part C. I just did it in my head though, so I probably made some mistakes. Where the heck is part C at? Yeah, here it is. So we should be getting this answer. Same from part C. But I'm actually doing it so I don't screw it up this time. Anyways, divide both sides by negative k. So t is negative ln of 1/7 all over what the heck k is, and then back substitute. So t is negative ln of 1/7 all over k, and we said k was negative ln of 23 over 39 all over 2. So this will equal 2 ln 1/7 all over ln of 23 over 39. And if you put that in your calculator, you get about 7.37 days until sort of that 0 hour happens. You really don't want to go outside because every other person then is going to be a zombie. And the probability of you also turning into a zombie will be the greatest in that perspective. So it's like if nobody, if at time 0 when there's only 25 zombies running around, the probability of you getting bit just isn't that big. But now at towards the end, it's like every other, or towards the middle, every other person is a zombie. So you best not go outside. Of course, when everybody's a zombie, you know you're going to have to defend yourself. If you go outside, you're going to be dealing with zombies, right? But I guess at this point, it's the most confusing. It's when every other person you don't really know if the person is a zombie or not. It's like flipping a coin. So, anyways, there's that. Hopefully, when the apocalypse happens, you'll be prepared as one of my math students. All right, thanks. Bye.